Welcome to Organic Chemistry, Chapter 1 on Structure and Bonding. In this chapter, we're going to review a number of topics that relate to concepts you've probably encountered in general chemistry. Before we get into those learning objectives, I want to just point out why I think organic chemistry is such a fascinating topic. I'm obviously an organic chemist. I have been for over 30 years studying organic chemistry. And I look at organic chemistry as primarily from the molecular point of view and how rich it is and the variety of types of molecules that you can encounter in nature. And here's one example of that. This is a molecule called luciferin. And this molecule is responsible for giving off light in the firefly. And you can see the photograph of the firefly here. Luciferin actually undergoes an enzymatic reaction with molecular oxygen, and it produces an intermediate that is an excited state when it forms, but then it decays and gives off light. So this is an example of bioluminescence. It's an organic molecule. You can see how it's constructed here. It has a number of carbons. These are all little carbons right here, 6 in a ring there. And you have some nitrogen, some sulfur, oxygen, and hydrogen. So we're going to be studying this as a topic in this class. We're going to talk about its structure, how it can be reacted, some of the reactions that it undergoes, how it might be synthesized in the laboratory if you wanted to do that, and some other properties of that molecule. So organic chemistry is very rich simply because of the richness of the molecules that exist in nature. And so here are the learning objectives for this chapter. You'll see a number of familiar topics in here, hopefully. For example, drawing and interpreting Lewis structures, looking at S and P atomic orbitals for different elements. We're even going to talk about molecular orbitals in this chapter and the geometry of organic molecules based on their bonding. So a lot of bonding fundamentals. And we'll talk about isomers and how they can be used to, how we can interpret different structures of isomers. So I won't be going over the details of these learning objectives now, but we'll refer back to those, and hopefully I will remind you of some of the, and quiz you on some of these learning objectives so that you have a good feel for what you need to learn in this particular chapter. So what are the origins of organic chemistry? I think you can trace a lot of the early organic chemistry to the German chemists. In fact, in 1828 here you can see there's a German chemist named Friedrich Wöhler who first made an organic compound that he identified as that. He took ammonium cyanate, which is shown here on the left. It's an inorganic salt. It's ammonium cyanate, and he heated it. And he heated it in the absence of oxygen, and it converted it into a compound called urea. And so urea is a nitrogen-containing compound. It's very important in things like fertilizer and things like that. But it's an organic compound. It has some carbon, nitrogen, carbon, double bond, oxygen. But this is a molecular organic compound. And this was an interesting transformation. They realized that you could take inorganic molecules and convert them into organic molecules, and that this would be a whole area, a whole discipline of study. Here's some other examples that are from your textbook of organic compounds, and you can see that a lot of these molecules have oxygen in addition to carbon and some nitrogen in here, but you can look at some of these and you can see here's a neurotoxin that's derived from the pufferfish. Here's ascorbic acid that could be obtained from a cranberry or some other type of fruit, vitamin C, right? Here's a natural dye that could be used for dyeing cloth, and is derived from a seed of a plant. And so then also you see morphine here, which is a painkiller that can be derived from poppies. So these are just some examples of organic molecules that we can talk about, and we can study their properties. So how do we give organic chemistry a definition here? What is organic chemistry? Well, it's a study of the structure and properties and reactions and preparation of carbon-containing compounds. So the key word here is carbon. And we're talking about molecules that have carbon-carbon bonds. But there are a number of other elements that could be incorporated into these organic molecules, including hydrogen, nitrogen. This gives you a list of that. We're going to talk about some of these. Sometimes we'll talk about phosphorus, silicon, and sulfur being incorporated in. But for the most part, we're going to talk about hydrogen, nitrogen, oxygen, and the halogens, things like fluorine and chlorine and iodine. How important is organic chemistry? Well, it's actually central to the economic growth of the United States. It's involved in the rubber industry, the plastics. That petroleum, for example, is a lot of organic molecules. So it's involved in the fuel industry, pharmaceuticals, synthesis of drugs, cosmetics, detergents, and the list goes on. So it's a very important area of study, and there are a number of jobs that you can find out there in industry that involve organic chemistry, and it probably is the number one discipline in terms of job opportunities in chemistry. It also forms the foundation of biochemistry and biotechnology and medicine. If you are involved in biology, or you are a pre-med student, if you are pre-dental, organic chemistry is really important in terms of understanding how you can use it and how you can use it to help your study in these areas, for example, of biochemistry and the role in life processes, for example, the structure of DNA or carbohydrates or something like that. So in industry, you can find jobs in biotechnology, chemical, consumer products, petroleum, and pharmaceutical. And if you want to find out more information about this kind of thing, you can go to a website that's published by the American Chemical Society, which is our professional society in chemistry. And you can find out more about job opportunities in organic chemistry. So let's take a look at some of the early scientists who were responsible for understanding at the beginning of what is organic chemistry. Here's a couple of them here. August Kekulé. He was responsible for actually understanding the structure of a molecule called benzene, which is a six-membered, six-carbon ring. And he discovered that carbon atoms are linked together to form carbon chains or rings. And he actually proposed that carbon is tetravalent. That is, that carbon could form 4 bonds to other elements. So it's tetravalent. We're going to be talking about that. Archibald Cooper was also involved in that recognition of carbon atoms linking to form carbon chains. Another scientist that I want to highlight here is Linus Pauling. In fact, Linus Pauling is a real stalwart in chemistry. He won actually 2 Nobel Prizes, and one in chemistry and one in peace for his anti-nuclearization proliferation work that he did. But he is involved in the study of chemical bonding and how it relates to medicine and biology. You may have come across Pauling's in another context, and we're going to be talking about his proposal of electronegativity of the periodic table. And so Pauling plays a really important role in organic chemistry. So let's talk about some fundamentals of the atom and the periodic table. You're familiar with the concept of a nuclide, an element, and its symbol. And just to remind you, if you have an element, X, this could be anything, right, like sodium or chlorine or anything like that, it's from the periodic table. You're going to have what is called an atomic number, Z, which is shown down below here as a subscript out in front of the X, and it identifies the number of protons in the element. And that actually identifies the element. That is, if I have 1 proton, then I know that that element is hydrogen. The other number above that, of course, is the mass number, which is the number of protons plus the number of neutrons, right? So protons, the number of protons identifies the element, and the number of neutrons will identify what particular isotope you have for that element. Let's take some examples since we're talking about organic chemistry. What about carbon? Well, there's three isotopes of carbon that are shown here: carbon-12, carbon-13, and carbon-14. Well, carbon-12 is sort of the standard here for the rest of the periodic table. And we can express its mass in atomic mass units, or AMUs. And it turns out that 1 AMU is exactly 1/12 of the mass of the carbon nucleus. And that has 6 protons and 6 neutrons in its nucleus. So this is the standard by which other AMUs are measured for the different elements. So atomic mass of carbon-12 is exactly 12 point, and you can see all the zeros here, AMUs. So this is really, we know this one very precisely because that's the standard element for AMUs. Now, how abundant is carbon-12? Well, you know that various isotopes have different natural abundances, and carbon-12 makes up 98.93% of all carbon in nature, so it's the major isotope, carbon-12. On the other hand, we have carbon-13. You can see it has 6 protons, but it has 7 neutrons to give a mass of 13. It's an isotope of carbon because it has a different mass. And its atomic mass is not exactly 13, but you can see here that it's got all these decimal places here, 13.003355 AMUs. What's its natural abundance? Well, its natural abundance is 1.07%. And so that makes up, these two together make up about 100% of the carbon in nature. Now you'll notice also here is carbon-14. What about carbon-14? You've heard of it, perhaps carbon-14 dating. It's a radioactive isotope with a half-life of 5,730 years, and it can be used to determine the age of organic molecules up to about 50,000 years old. So if you want to date a piece of wood, you could use carbon-14 dating to do that. Now, carbon-14 is not a significant isotope in nature. It forms only a trace of all carbons, so it's certainly less than 1%, and it's a very small amount of all carbon, but it can be used usually to date other materials. So if we look at the periodic table, here's a section of the carbon of here off the periodic table. You'll notice atomic number is 6 protons. Here's the symbol. Here is the electron configuration. We're going to talk about that a little bit. And its physical state, its crystal structure. But here's an important thing here. What's the atomic weight? Well, the atomic weight of carbon on the periodic table is 12.011. And remember that this is an average atomic mass of carbon. And how that can be calculated is to take the percentage of carbon-12, or 0.9893 times 12, and add it to the percentage of carbon-13, and that's 0.0107 if you put that in a decimal form, times its atomic mass, and you actually get then the average atomic mass of carbon, and this is what is listed on the periodic table for the various elements. So it's a weighted average of the masses of the different isotopes.